before we start approximating things, let's look at an exact thing. So let's evaluate the integral from 2 to 6 of the natural log of x. Okay, well, that's an integration by parts problem. And let me do one more thing here. Sorry, one sec. I can always mess with things in the beginning of class. There's too much light in here. You guys can see the board okay. So I'm going to do the integral from 2 to 6 of natural log of x dx, just the regular way where we actually find the antiderivative. For the integral of natural log of x, which I would do without the limits of integration, we have to do an integration by parts where u is the natural log of x, dv is dx, du is 1 over x dx, and v is equal to x. So then this is going to be equaling uv, which is x natural log of x, minus the integral of v times du, which is x times 1 over x times dx. But x times 1 over x is just 1, and the integral of 1 is just x. So this ends up equaling x natural log of x minus x. So then this is going to be x natural log of x minus x evaluated between 2 and 6. And then plugging in those limits of integration, we get 6 natural log of 6 minus 6 minus 2 natural log of 2 minus 2. And minus 6 plus 2 is minus 4. So we can simplify this as 6 natural log of 6 minus 2 natural log of 2 minus 4. And that would be our exact answer. And if we wanted a decimal approximation, we could use a calculator and show that this is approximately 5.36. Great. One of those is a little sniffly here. All right, 1 second. Okay. So now what we're going to do is we're going to use the trapezoid method to approximate the area under this curve and see kind of like how that differs from our actual value. So let's go ahead and say we're going to approximate the same integral from 2 to 6 of the natural log of x dx using the trapezoid rule method. With n equal to 4 trapezoids. Okay, so there's a formula you probably, I don't know if they're going to give it to you or you can memorize it, but I kind of want to explain where the formula comes from, but then I really want to emphasize that you should memorize the formula if you memorize it. So here's the deal. Oh, yeah, all right. So let's draw some things. So I'm going between 2 and 6. 1, 2, 3, 4. Natural log of 1 is 0. Natural log of 2 is, I don't know, it's about 0.7. So it's starting about right there. And the natural log of 6 is natural log of 2 plus natural log of 3. I don't know. It's something a little bit larger. Yeah. It's like that. So here's what my curve looks like, essentially. And I'm trying to find the or approximate the area under this curve using trapezoids. So in each of these, so I'm breaking up into 4 sections. So first of all, my delta x, right, the width of each trapezoid or subsection in general, my delta x is 6 minus 2 over 4. Right, it's your total length divided by how many rectangles or trapezoids, which is going to be 1. So 2 to 3, from 3 to 4, from 4 to 5, from 5 to 6. So these are my delta x's. And for each of these regions, I'm going to draw the trapezoid. So I'm going to connect this point straight to that point there. which is a little bit under the curve. All these are a little bit under the curve because the curve is kind of concave down. I mean, maybe it's hard to see because of how close it runs, so I'll try and make it a little bit exaggerated here. So in this case, I already know, not that it matters really, but I already know I'm expecting an underestimate. Because the area of these trapezoids looks like it's going to be less than the area under the curve. How do we find the area of a trapezoid? So if you draw, I'm going to draw the trapezoid. I'm going to draw this trapezoid, which looks like this for a second. I'm going to draw it like, I'm going to turn it 90 degrees and draw it like this. So I have a trapezoid, and the area of a trapezoid is this length, which I'm going to call the base, right? Because I'm calling, right, this is my delta x. It's your delta x times the average of those two lengths. So if I call this length 1 and this length 2, it's the average of length 1 and length 2. And the way you can think about that is if basically if you cut this little triangle part off here and swivel it around to being up there, you get a rectangle. And the height of the rectangle is delta x, and the length of the rectangle is the average of those two lengths. So if I want to find the area of each trapezoid, well, the area of each trapezoid is going to be the base, which is delta x, times, okay, the area of this trapezoid is going to be, well, I already have the base, I just need essentially the average of the heights. So the average of the heights is going to be f of 2 plus f of 3 divided by 2. And for the second trapezoid, the average of the heights is going to be f of 3 plus f of 4 divided by 2. And then for the third trapezoid, it's going to be f of 4 plus f of 5 divided by 2. And then for the last trapezoid, it's going to be f of 5 plus f of 6 divided by 2. So what we're going to do is we're going to factor out the 1/2, or the dividing by 2. So we're going to write this as delta x divided by 2. And then I have 1 f of 2. But I have 2 f of 3s. I have 2 f of 4s. I have 2 f of 5s. Oops, I forgot the 2 there. I said 2 of them, but I didn't write it. And I have 1 f of 6. So this is, so you don't actually know where the formula comes from, although it's nice to see it. But when you're doing the trapezoid method, the rule is that you're always going to do your delta x divided by 2. And then for each of your endpoints, you're going to do the first one and the last one just one of. So you have 1 f of 2 and 1 f of 6. And then all the middle ones you have 2 of. So the pattern is 1, 2, 2, 2, 2, 2, 2, 2, 2, 2, 1. So the ends are 1s and all the coefficients of the inner ones are 2. That's what I remember. 1, 2, 2, 2, 2, 2, 2, 2, however many points you have, 1. So if you're doing n equals 4, you should have 5 points, right? Because you have 4 sections, you have to have an endpoint, so 5 points. So you should have a 1, a 1, and then the 3 middle ones should all have 2s. So this particular one, you're going to get delta x, which is 1 over 2, times f of 2, which is natural log of 2, plus 2 natural log of 3, plus 2 natural log of 4, plus 2 natural log of 5, plus natural log of 6. And if we get out of the calculator, that's approximately 5.34. Okay, looking back to our previous one, our previous answer was about 5.36. So our error, and so when you find the error, you should always write it as a positive number. So the error is going to equal, usually we just put absolute values around and say, okay, it's the absolute value of that one minus this one, or this one minus that one. It doesn't really matter which order you decide to subtract in. But it does matter that your final answer is positive. So 5.34 minus 5.36 is negative 0.02, but then the absolute value of that is 0.02. So that's our error using this method. Now, yeah, we might as well talk about the error approximation. So the other thing we talk about when we talk about using a method of approximation is the thing is pretending like we're actually using this to approximate something we don't know how to integrate or are not able to integrate. Then the question becomes, well, how big could your error be? Right? Because if you don't actually know what the area is, because you couldn't actually do the integral, then we want to know, well, how much might we be off by? And there is a formula for that. And again, I don't know if the professor is going to provide these formulas or not. Usually I feel like the error formula, like if I was teaching the class, my expectation as a teacher would be that you know the actual trapezoid and Simpsons rule formula, but that you do not have to memorize the error formulas because they're kind of a pain in the butt. But hopefully your teacher will say words about what they expect as far as formula memorization. Some people like to give everything, some people are like, no, you memorize it all. So be aware, your teacher will probably have some expectations. So for the trapezoid method, the error using the trapezoid method in absolute value, so make sure it's always positive. The error is always going to be less than or equal to the following quantity. I should be a little more specific. For the integral from a to b of f of x dx, the error using the trapezoid method is going to be less than or equal to b minus a cubed divided by 12n squared times the absolute value first, yeah, of, that's the same either way, of the max of, no, that's actually written incorrectly. Yeah, sorry, I've got it written slightly differently. It's actually the maximum of the absolute value of the second derivative of your function, where x is between a and b. So a lot of the time, hopefully most of the time, it's going to be pretty easy to tell what's going to make this as big or as small as possible. So let's figure out what we've got here. So first of all, for this integral, the integral from 2 to 6 of the natural log of x dx, we know that, we know that our error is going to be less than or equal to 6 minus 2 cubed divided by 12 times, we used n equal to 4. And then we still have to figure out what the maximum of the absolute value of the second derivative is. So let's take the derivative and then the second derivative. So if my function is natural log of x, my first derivative is 1 over x. My second derivative is negative 1 over x squared. So it actually is important that we say it's the maximum of the absolute value. So if I said it was the absolute value of the maximum of this on the interval from 2 to 6 is when you plug in 6, because you get negative 136, which is the biggest it could be because it's the smallest negative number. That's not what we want. We want to say, well, I want to find the maximum of the absolute value of negative 1 over x squared, where x is between 2 and 6. So I want to ask myself, and I'm asking you guys this question right now. Between 2 and 6, what's going to make this fraction the biggest? Is it going to be the 2 that makes the denominator small, or is it going to be the 6 that makes the denominator large? So what value of x do I want? Is it 2 or is it 6? James has picked up his water, meaning he's waiting for you guys to answer. So let me ask the question again. Which of these values of x, 2 or 6, is going to make this quantity the biggest? If I plug in 2, I'm going to get the absolute value of negative 1/4. If I plug in 6, I'm going to get the absolute value of negative 1/36. Which is bigger? Let me ask you guys a question. I don't mean this insultingly, I'm just really here. Are you there? Is my video working? Can someone type something in the chat so I know you guys are there? Thanks. Awesome. Perfect. Appreciate it. I just want like sometimes there have been occasions where my coworkers like my video actually stopped working and I asked students to write something in the chat and no one did. I was like, oh no. So I'm glad you're there. And it is 2, yes, because the 2 is going to make this thing the biggest, right? Because it makes the denominator the smallest. Thank you. And that's but we need the absolute value, right? Because the absolute value, we want it to be the biggest in absolute value. So the maximum of this is 1/4. Now, most of the time with these problems, you will typically have a function whose second derivative is either always increasing or decreasing. So it'll be really obvious you pick either the left endpoint or the right endpoint to make it as big as possible. Most of the time. So that's the maximum of that, 1/4. Now let's say these numbers are going to turn out really nice. Because up here I've got a 4 cubed, and down here I've got a 4 squared times 4. So that 4 cubed cancels with that 4 cubed. And my error is less than or equal to 1/12, which I believe is approximately what, 0.0833. I'm pretty sure that's right. So that's the biggest the error for the trapezoid method could be. I erased what our answer was, but our error was actually 0.02. So all this formula gives you is an upper bound on how large your error could be having used whatever number of trapezoids you used. Is there anything else I want to say about that? So before we get into Simpson's rule, which we will do next for the same problem, I want to do one more thing, which I think is worthwhile. It goes along with this. Which is, So the other question I want to ask, and so I'm going to have my f double prime up here, f double prime of x, still, absolute value negative over x squared. The other question people like to ask is, how large does n need to be to guarantee an error less than, usually for these ones people use scientific notation, so less than something like 10 to the negative 4th. So in this case, we know all the information in this formula except for what n is. So what we're saying is we still have the same b and a, right? It's the same integral from 2 to 6 of natural log of x dx. So our error formula is still 6 minus 2 cubed over 12 times, we don't know n squared, times the maximum of this, which is still 1/4. Because we're still on the same interval with the same function. But then we want this to be less than or equal to 10 to the negative 4th, or 1 over 10 to the 4th. Yeah, I like 1 over 10 to the 4th. Okay, so then we're going to try and solve for n squared. So typically what I'm going to do is I'm going to multiply both sides by n squared and both sides by 10 to the 4th. So I'm going to say, and then I'm going to simplify a little bit too. So here I've got 4 cubed over 12 times 4 times 10 to the 4th should be less than or equal to n squared. I can cancel a 4 here and a 4 here and a 4 here. So I really have that n squared needs to be bigger than or equal to 4/3 times 10,000. So that n is bigger than or equal to the square root of 40,000 over 3. Then we get out a calculator. We look at 40,000 divided by 3, and we take the square root of that. And we get 115.47. So n is bigger than or equal to 115.47. So we say that n is going to be 116. We always round up to the next one, right? Because we need n to be at least this big. We need n to be at least as big as 115.47 to guarantee that our error is less than 1 over 10 to the 4th. But you can't pick 115.47 trapezoids. you have to have an integer number of trapezoids. So we round up to the next integer. So there's an example of the trapezoid method and kind of all the trappings that go along with it. Let's go ahead and talk about Simpsons method. So what I'm going to say is, what we're going to do for Simpsons method is pretty much the same stuff we just did with the trapezoid method. It's the same idea, you're using the same concept, you're doing the same thing with the error, it's just the formula is different. So if the trapezoid method stuff seems logical, like if that was understandable, then the Simpsons method stuff should also make total sense. But what if there's some confusion here, the Simpsons method will give us a good opportunity to kind of revisit that, and you can ask questions like, James, why are we doing this thing? Again, the trapezoid method formula is this 1, like this 1, 2, 2, 2, 1 pattern of coefficients. The Simpsons method formula is a little bit different. And let's see what I want to do here. So make sure. Yeah. I just wanted to see one thing. Okay. Yeah, I guess I could. I'm going to redraw the picture. So something interesting about Simpsons method, which is not true for any other method, is that Simpsons method requires that you absolutely have to have an even number of intervals yeah, your n has to be even, right? You're dividing up an even number of subsections. So we're going to approximate this using Simpsons rule. So the thing on Simpsons rule, here's the idea behind Simpsons rule. So for my logarithm function, which I'm going to draw in a kind of exaggerated way, just to kind of make it easier to see what's going on here. Let's say this is my logarithmic function from 2 to 6. Simpsons rule uses 3 points at a time. So if I'm breaking this up into 4 equal subsections, right, I'm using the first 1, 2, 3 points. I'm using this point and this point. And the idea that we're using here is that there is actually a parabola. We're not going to find it, but there is a parabola that goes through those 3 points. And maybe, I don't know, maybe it looks like this. Let me draw it in a different color. Right, maybe the parabola that goes through those 3 points looks like that. And then through the next 3, so then we use those 3 points, and then for the next 3 points, here, here, and here, so here, here, and here, there's a different parabola that goes through those 3 points. And maybe it totally defies our expectations and looks, you know, something like, I don't know. It's hard to draw these parabolas. Maybe it looks like that. I don't really know exactly, but there is a theorem that is true in mathematics that says any 3 non-collinear points, meaning they're not on the same line, any 3 points that are not on the same line, you can always find a parabola, one parabola that goes through them, which is kind of neat. So what Simpsons rule does is it tells you the area beneath the parabolas. So Simpsons rule tells us for these 3 points how much area is under that parabola, which is a good approximation of the function. And for these 3 points, tells us how much area is underneath that parabola. And that's why you need an even number of points, because you have to be able to essentially chunk it into things of 2, right? You need 2 subsections here to get 3 points. You need 2 subsections here to get 3 points, and so on and so on and so on. So I will say it one more time, at least. For Simpsons rule, you have to have an even number of subsections. You cannot do it with an odd number. So the Simpsons rule is a little more complicated. Here's how it works. So the area approximation for Simpsons rule, which we're going to write as S4, right? Simpsons rule with n equal to 4 subsections. That's going to equal your delta x divided by 3. And then for the trapezoid method, the pattern is 1, 2, 2, 2, 2, 2, 2, 2, 2, 2 forever, and then 1. For Simpsons rule, the pattern is 1, 4, 2, 4, 1, 1, 4, 2, 4, 2, 4, 2, 4, 2, 4, 2, 4, 1. So it's symmetric. It's 1, 4, 2, 4, 2, 4, 2, 4, 2, 4, 2, 4, 1. Right? It's always alternating between 4s and 2s, but you always have a 1 next to a 4. And then 2, 4, 2, 4, 2, 4, 2, 4, 2, 4, and then 1. So here's the pattern. Here's why it works this way. For the first parabola, it's f of 2 plus 4 times f of 3 plus f of 4. This is not a formula I've ever verified, but the area under this part here is f of 2 plus 4 times f of 3 plus 1 times f of 4. And then the area under this parabola is going to be f of 4 plus 4 times f of 5 plus f of 6, which then becomes the pattern 1, 4, 2, 4, 1. So we end up getting delta x, or delta x is still 1 here, right? It's still 6 minus 2 over 4. So it's going to be 1 over 3 times f of 2 plus 4 f of 3 plus 2 f of 4 plus 4 f of 5 plus 1 f of 6, which ends up being 1/3 times natural log of 2 plus 4 natural log of 3 plus 2 natural log of 4 plus 4 natural log of 5 plus natural log of 6, which is approximately a number I didn't calculate. We can calculate it if we want, though. Let's find out. We get natural log of 2 plus 4 natural log of 3. Doing this with a pen in your hand is less than ideal. Plus 2 natural log of 4 plus 4 natural log of 5. I missed my TI 85 calculator, or TI 83. That was my favorite calculator. This calculator is less user friendly. Divided by 3, we get approximately 5.36, which is a lot closer to the actual, right? When we calculated the actual natural log, it was about 5.36. So typically Simpson's method is always a better estimator than the trapezoid method, which is kind of good to know. Hopefully you guys can see, I don't know, maybe it's not super clear, that, right, if you continue this pattern, right, like let's say we wanted to, instead of doing 4, we wanted to do 8. So I broke it up into, 8 subsections. So I did that. That's what I point out, that if we did it that way, right, then our Simpsons rule using 8, well, our delta x would be different. Right? Our delta x would be 6 minus 2 over 8, which is 1/2. So our delta x over 3 would be 1/2 over 3. And then we'd have, for the first, 2, 2.5, and 3, we'd have f of 2 plus 4 times f of 2.5 plus 1 times f of 3. And then that's our first parabola. And then for our second one, we'd have f of 3 plus f of 3.5, 4 f of 3.5 plus 1 times f of 4. That's our second parabola. And then we have plus, for our third one, 4, 4.5, and 5. So it'd be f of 4 plus 4 f of 4.5 plus f of 5. That's our third parabola. And then finally, lastly, we'd have f of 5, and then talk about 5 and 6. So we'd have f of 5 plus f4 times f of 5.5 plus f of 6. I'm really just showing this to show you that you really do get the 1, 2, 4, 2, 1, the 1, 2, 4, 2, 4, 2, 4, 2, 1 pattern, right? We've got 1f of 2 plus 4f of 2.5 plus 2f of 3 plus 4f of 3.5 plus 2f of 4 plus 4f of 4.5 plus 2f of 5 plus 4f of 5.5 plus f of 6. So it really is 1/2 over 3, so 1/6 times f of 2 plus 4f of 2.5 plus 2f of 3 plus 4f of 3.5 plus 2f of 4 plus 4f of 4.5 plus 2f of 5 plus 4f of 5.5 plus 1f of 6. If we're not going to calculate, but I just want to point out that, right, it's always this 1, 4, 2, 4, 2, 4, 2, 4, 1 pattern. Okay. So if we used, let's say we used, yeah, we can do that. So let me ask the same sorts of questions. If, all right, so for this integral, if n equals 4, what's the maximum error? Well, our error was already pretty small, right? I mean, both our estimate and our actual value were both the same to 2 decimal places. So our error is probably going to be less than 0.01, at least I would think. Yeah. Let's check. I could be wrong about that, though. I'm always kind of a little sketchy on the error stuff. Well, let's go ahead and figure out what our error is. So the error formula for the Simpsons method is similar, but not quite the same. It's less than or equal to, b minus a to the 5th power over 180 n to the 4th times the maximum of the absolute value of the 4th derivative on the same interval. Ooh, that's quite a formula. So then let's see. If we do this, we're going to get, their error is less than or equal to b minus a, so 4 to the 5th divided by 180 times 4 to the 4th. Okay, well, that's convenient because a lot of those 4s will cancel out. And then we got to take the maximum of the 4th derivative. Okay, so we know that our first derivative is 1 over x. Our second derivative is negative x to the minus 2nd. Our third derivative is 2x to the minus 3rd. And our fourth derivative is negative 6x to the negative 4th, or negative 6 over x to the 4th. And the nice thing about something like this is it's still relatively easy to see that if you're taking the absolute value, well, you don't need the negative, right? The absolute value of negative 6 over x to the 4th, since x to the 4th is always positive, that's just going to be 6 over x to the 4th. And this is going to be as big as possible when x is as small as possible. So we're going to let x equal 2, because that's the smallest number on our interval. And we're going to get 6 over 2 to the 4th. That's going to be the maximum of the absolute value, which reduces to 3/8. So that's going to be 3/8 there. And then we can cancel a 4 here and a 4 here. So our answer is 3 over 360, which is definitely less than 3 over 300, which is 0.01. Sorry. Right, this is less than 3 over 300. Our denominator got smaller, our fraction got bigger, and that's equal to 1 over 100, which is 0.01. Okay. You could actually find the number, but it's not super important. Let's ask the other type of question. How big does n need to be? So I need more room. So how big does n need to be so that the error when using Simpson's method is less than 10 to the negative third. Double check one thing. Yeah. Okay, so we're just taking that same equation, this error equation, and saying it's going to be left. We're saying we don't know what n is, so we're not going to plug in 4 for n. And we're just going to set this to be less than 0.001, 10 to the negative third. So I'm going to set 180. Sorry, that goes on the. All right, this formula always right here. I'm going to set 6 minus 2 to the 5th divided by 180 n to the 4th times that maximum value we just found, which was what was it? 3/8, right? 6/16, yeah, 3/8. That's the error using the Simpsons method. And I want that to be less than or equal to 0.001, which is 1 over 1,000. So again, I'm going to multiply the n to the 4th up there and the 1,000 over there. So let's see, I've got on this side 4 to the 5th times 3 over 180 times 8 times 1,000 has to be less than or equal to n to the 4th. We can simplify this a bit. I can cancel a 3 here and a 3 here. I can cancel a 4 here and a 4 here. I can cancel a 4 here and another 4 here. So it looks like I've got 4 to the 3rd, so 64 times 1,000 over 15 times 2. That seems about right, I think. Sure, yeah. So then that's got to be less than or equal to n to the 4th. So n has to be bigger than or equal to the 4th root of that number, 64,000 over 30, or 6,400 over 3. Using a calculator, we get that that's about, so n is greater than or equal to about 6.796. So let me ask you guys, what does n actually have to be bigger than or equal to? What am I going to choose for n? What am I going to round up to? I will warn you, it is a slightly tricky question. You might be thinking, we're going to round up to 7 because, well, duh, right? The next biggest number is 7. And that would be incorrect because for Simpson's method, what does n have to be? N has to be, you guys know it, I said it like 10 times. You guys are very interactive today, more so than usual. N has to be even. So for Simpson's method, if you're finding how big n has to be so that your error is less than the number, you have to round it up to the next biggest even number. So just be aware of that. Okay, so let's look at kind of a more standard example. So this example is fine, except again, natural log of x is totally a function we know how to integrate. So let's look at one more example where the function actually is, I always forget this word. The function can't be integrated, which there is a word for. I think it's called being not elementary. I don't actually remember. So yeah. So here is an integral that can't be done. Integral from 0 to 1 of e to the negative x squared. That thing cannot be anti-differentiated. So I want to find n so that our approximation using the trapezoid rule. Our approximation is accurate to within 0.001. So all I'm saying here is I want my estimate of the error for the trapezoid method. I want that to be less than or equal to whatever it's less than or equal to, and I want that to be less than or equal to 0.001. And again, for the trapezoid method, the formula is b minus a cubed over 12n squared times the maximum of the absolute value of the second derivative. Okay, that's not too bad. B minus a is just going to be 1 over 12n squared. We have to figure out the maximum of the second derivative here. Okay, the second derivative is kind of a pain in the butt. So our first derivative of e to the negative x squared, where that's your function, is going to be e to the negative x squared times negative 2x. Okay, so far so good. Our second derivative, we have to use the product rule. So the derivative of just e to the negative x squared is, again, e to the negative x squared times the negative 2x. But then you have to multiply the derivative of that by that. And then plus, now it's that, times the derivative of that. Which is equal to, let's see, I can factor out e to the negative x squared. It's e to the negative x squared times 4x squared minus 2. And so here's where we get a little hand waving. I don't actually know what value of x is going to make this maximal. Let me show you what I mean. I'm going to write this as 4x squared minus 2 over e to the positive x squared. To make this fraction as large as possible, I would, oh, that's interesting. I hadn't thought about that. Huh. It's kind of cheating. Interesting. So really what we should do, technically, is, and some people will do this, which we really shouldn't do, but some people will actually take the next derivative and say, so if I want to find where this second derivative is maximal, well, to find where a function has a maximum, you take its derivative, you set it equal to 0 to find the critical values, and we don't want to do all that. The nice thing here is we can get an upper bound. We can estimate the maximum. So here's the thing. I've got a fraction. I want to make this fraction as big as possible. To make the fraction as big as possible, you make the bottom as small as possible and the top as big as possible. So on the interval from 0 to 1, if I let x equal 1, that's going to make the top as big as possible. And this is a totally legit, we're not just making stuff up, right? This is a legitimate method of saying I can put an upper bound on this. So I'm going to make the top x equal to 1, so I get 4 times 1 squared minus 2. And I'm going to make the bottom x equal to 0, because e to the 0 will be the smallest e to the x squared can be. So if x is 0, I get e to the 0 squared, which is just e to the 0, which is 1. So this is going to equal 4 minus 2 over 1, which is 2. And so what I'll say here is, while this function while the second derivative might not actually get to be as big as that, 2 is certainly bigger than that can actually be. And that's good enough. So yeah, so what we're going to say here is, we're going to have b minus a cubed, so 1 cubed over 12n squared times 2 has to be less than or equal to 0.0, which I would prefer to write as 1 over 1,000. Then we cross multiply. Really, we multiply the n squared up here. We multiply the 1,000 up here, so you get 2 times 1,000 over 12. And then n has to be bigger than or equal to the square root of 2000 over 12, which is 1000 over 6. That number is approximately 12.9. So n has to be bigger than or equal to 13. Not 14, right? It's not Simpsons method. This is the trapezoid method for odd numbers of 10. Okay. Questions about anything I said? Got a little chip in my nail. Let's feel if I can go file my nail later. That's really kind of all there is to Simpsons method and trapezoid method, right? You've got the approximation formulas, you've got the error formulas. That's kind of it. So we can do more examples if you guys want, but we have what? We have 30 minutes left. We should probably move on and talk about the discrete probability stuff that you guys are getting into. So let's go ahead and go there. Again, if you want to see more examples of this, you're certainly welcome to ask, but I will certainly say there's not much more to say, right? There's just doing more examples using the same formulas again and again. Not that that's not worthwhile. I just don't think it's the best use of our time together. Okay. So let's go ahead and take a look at expected value. By the way, expected value, just another word for average or mean, standard deviation, and variance. So let's look at some examples. Let's find the average, sure, of some really, really varied test scores. Of the test scores, maybe these are like how people rated some products, because I would hopefully not see these test scores in class. Of test scores 0, 0, 100, 100, 80, and 20. Some people really didn't know anything. Some people knew everything, and one person knew most of it, and one person knew not much of it. Okay, so the way you find the average of any number of things is you add them together and divide by how many there are. So the average, and there's like so many different notations for the average or the expected value. So the expected value, the average, the mean. So if I had to give names to each of these notations, this is definitely the expected value. This is the notation for the mean. It's the Greek letter mu, and this is the x bar, which is usually used for the average. But they literally all mean the same thing. I should back up a tiny bit. In stats, these have slightly different meaning, or like this is your actual average of your population, and this is like your estimated average. But we're not in stats, right? This is just math. So all these notations have the same sort of meaning. They mean find the average of the thing. And the average is just going to be 0 plus 0 plus 100 plus 100 plus 80 plus 20 divided by 1, 2, 3, 4, 5, 6. That's going to be 300 over 6, which is 50. Great. More generally, you could also write it like this. I'm thinking of this as 0.6 plus 0.6 plus 106 plus 106 plus 86 plus 26. My favorite word to say it. Which I'm actually going to write as 0 times 2/6 plus 100 times 2/6 plus 80 times 1/6 plus 20 times 1/6. An average is also called a weighted average, because you're essentially taking each score and multiplying it by the probability that it occurs. So this is, and I wrote this, yeah, sure. This is x1, so right, the score x1 was 0, and this is the probability of getting a 0. And we could say, so 0 is our x1 score, 100 is x2, and the probability of getting 100 is 2/6. And then 80 is the third possible score, and 1/6 is the probability of getting that third possible score. And 20 is the fourth possible score, and 1/6 is the probability of getting that score. So when you're writing the expected value of something, a more general way of writing it is it's each possible value times the probability of that value occurring. And we often use sigma notation for this, summation notation, where you write it as the sum from I equals 1 to 4 in this case of x sub I times the probability of x sub I. That's all an average is. An average is just each thing multiplied by the probability that it occurs. So that's why it's called a weighted average, right? Because the higher probability that something occurs, the more weight that particular score gets. Okay. Variance, the word literally means, right, how much varying there can be, is a measure of how much variation there is from your calculated average or expected value. So here's how we calculate variance. Variance, for the same example, right, where our scores are 0, 0, 100, 100, 80, and 20, and the expected value we just found out was 50. The variance, we want to measure how far away we are from the mean and still kind of count the number of, right? So we have 2 scores that are 50 away, 2 scores that are 50 away, 1 score that's 30 away, 1 score that's not 30 away. But we don't want, like, the problem is if we just kind of said, like, I'm going to do the differences from the mean and add them all up, you would get 0, right? Because some of them will be negative, some of them will be positive, and they all balance each other out. So to kind of not have to deal with the fact that we can either be larger or smaller than the mean, we're going to take our differences and then square them so that all the differences are positive. The variance, v of x, is going to be all of our differences squared. So 0 minus 50 squared times the probability of getting a 50, which is going to be 2/6. Sorry, the probability of getting a 0. And then it's also going to have 100 minus 50 squared times the probability of getting 100, which is also 2/6. And then we're going to have 80 minus 50 squared times 1/6. And then we're also going to have 20 minus 50 squared times 1/6. Which, more generally, the formula for this looks like x1 minus, we can use any notation we want. I'm going to use the mu notation. So x1 minus the mean squared times the probability of x1 plus x2 minus the mean squared times the probability of x2, and so on. x3 minus the mean squared times the probability of x3 plus x4 minus the mean squared times the probability of x4. So that is your general formula for the variance. Also, most calculators, if you input a set of data, will tell you the expected value of the variance with like a push of a button. And this ends up being, so right, calculating this, it's kind of a gross, all right? This is going to be 2,500 times 2/6 plus another 2,500 times 2/6. 80 minus 50 is 30, squared is 900 times 1/6 plus another 900 times 1/6. This ends up being equal to 1,967. I think it's actually equal to. The problem with variance is it kind of, it's kind of a number that where you're squaring your differences, so it doesn't have a whole lot of specific meaning. So often after we find the variance, we then take the square root of it. So the square root of the variance is the standard deviation, which you use the Greek letter lowercase sigma for. That's your standard deviation. So in this problem, the standard deviation would be the square root of 1,967, which is approximately 44.3. And that represents how far each test score is from the mean on average. Right? So on average, the test scores are 44 points away from the mean. That doesn't really say a whole lot, right? Because some of them are, well, I mean, it kind of says, I don't know, some of them are 50 away from the mean, some of them are 30 or 30 away from the mean. I guess that says something semi-meaningful. On the other hand, if all 6 scores were 50, so if we had test scores that we know 50, 50, 50, 50, 50, 50, not very exciting, but at least nobody did terribly. I mean, okay, 50, right? We're not, and none of us are hoping to get a 50 on the test, probably, right? We're usually hoping for a higher score than 50. Still, nobody totally didn't know anything when they took this test. Here, the average would be 50, big surprise. And the standard deviation would be 0. And the variance would also be 0. Right? Because there's no deviation from the mean. Everyone got the same exact score. So that's a very quick breakdown on mean, standard deviation, and variance. But now we're going to be talking about these more in the context of being given some probability distribution. Discrete. So I think reading that email from Ma again, I believe he said only discrete and not continuous, but let me double check just to make sure. Discrete probability, he doesn't say continuous. So we don't need to get into continuous just yet, but continuous is definitely on the way. So discrete probability, when someone says the word discrete, you should think of like a finite number of things can happen. So flipping some number of coins, for example, is a discrete situation where there's only a finite number of possibilities. Where if, on the other hand, if someone said like, we're measuring people's heights or how much time it takes for something, those are both examples of continuous variables because you can literally have an infinite number of possible heights or an infinite number of possible time values, right? And you're like, well, so if time was measured between like 0 and 30 minutes, you might say like, James, there's not like an infinite number. I'd be like, oh, ho, ho, there is an infinite number. Right? There are an infinite number of time possibilities between 0 and 30 minutes. And the reason is because you can break that up into any kind of small increment that you want. Same is true with height, right? Literally from being 4 feet tall to 7 feet tall, there are technically an infinite number of height possibilities depending on how finely you measure things. Now, if you only want to measure to like the nearest half inch, okay, then you've limited yourself to a finite number of kind of ranges. But things like height, things like time, things like weight, technically there are an infinite number of possibilities if your measurement is as fine as you want it to be. But then there are discrete things like, let's say we flip 4 coins. 4 fair coins, right? Whereas there's an equal chance of a coin coming up heads or tails. And let's let X equal the number of heads that come up. Let's find the probability distribution for X. So first we're going to list the sample space. Meaning the set of all things that can happen. While I'm flipping 4 coins, I can either get 0 heads or 1 head or 2 heads or 3 heads or all 4 heads. Those are the possibilities. But we want to kind of list each possibility within those. So if I'm getting, say, X equal to 0 heads, well, there's only one way to get 0 heads. All 4 coins came up tails. Okay. But what about one head? Well, now for one head, there's actually a number of ways you can get one head. If you're thinking of all the coins to be right. Let's say your coins are all different colored. Someone dyed 4 coins, red, yellow, green, and blue. And the first one, right, the green coin comes up. And then the next time you flip them, the yellow coin comes up heads. And then the next time you flip them, the red coin comes up heads. And then the next time, the blue coin comes up heads. There's actually 4 different ways to get one head with 4 coins. What if you have 2 heads? Okay, so this is where your ability to list things out in a systematic way actually is kind of important. So when I'm trying to figure out two heads, I'm going to do it this way. I'm going to start with my heads all the way to the right. So tails, tails, heads, heads. And basically my kind of method is to let this one that's furthest to the left keep moving to the left until we're done, and then move this other one over and the other one back all the way. So I'm going to move this one over and get tails, heads, and then move this one over and get heads, tails, tails, heads. Now I've moved this one as far over as it can go, so I'm going to move this one over, but I'm also going to move this one back as far as it goes, but not over to the other side of that one. So I got tails, heads, heads, tails, and then move this one over to the left, heads, tails, tails. And the only thing I can do is move this one up next to it. Heads, heads, tails, tails. And these are the 6 ways you can get 2 heads and 2 tails within 4 coins. For x equals 3, it should be clear, or maybe not. After we do it, it should be clear. The number of ways of getting 3 heads is the same as the number of ways of getting 1 head. Because if you're getting 3 heads, it's the same as having to figure out how to get 3 tails, which is the same as 1 head. So you can have, I'm just going to interchange tails and heads. So I'm going to get heads, 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 tails, or heads, heads, tails, heads, or heads, tails, heads, heads, or tails, heads, heads, heads. And then finally, if I want all 4 being heads, there's only one way to get all 4 being heads. Great. How many things are in our sample space? 1, 2, 3, 4, 5. Well, let's see. 1 plus 4 plus 6 plus 4 plus 1. That's going to equal 16, which shouldn't be a surprise because the number of total possibilities, well, for each coin, there are 2 possibilities, heads or tails. So we've got 4 coins, and the number of possibilities for the first one is 2 times 2 for the second, times 2 for the third, times 2 for the fourth, which is 16. So there are 16 possibilities when you flip 4 coins. There are 32 possibilities when you flip 5 coins. So now we can make the probability distribution table. It looks like this, and there are definitely tables like this in your textbook, in your homework. So in the top column, we have the values of x, and the bottom column, we have the probability of x. So x could be 0, 1, 2, 3, or 4. And the probability of getting a 0 is 1 in 16. The probability of getting 1 head is 4 in 16, which, yes, I know you could reduce to 1/4. The probability of getting 2 heads is 6 in 16. Probably getting 3 heads is 4 out of 16. And probably getting 3 heads is 4 out of 16, and 4 heads is 1 out of 16. And here's something that's always true. If you're talking about a probability distribution, all the probabilities should be non-negative. In fact, really, this should be positive. If the probability of something happening is 0, you probably shouldn't actually include it in the things that can happen because it doesn't happen. So typically, all of your probabilities are between 0 and 1. There should be a non-zero chance of a thing happening that we're talking about happening. And I guess it could actually be all the way up to equaling 1, right? There could be just one thing that happens. There's 100% probability that happens. And the second thing that has to be true is that if you add up all the probabilities, they have to add up to 1. So the sum of your probabilities has to equal 1. Right? If you take into account all the things that can happen, there should be 100% chance that one of them happens. So when you add up all the things that can happen, if you add up all the probabilities, it should add up to 100%, which it does. 1/16 plus 4/16 plus 6/16 plus 4/16 plus 1/16 is 16/16, which is 1. And then we can ask questions like, yeah, we got room. What's the probability that x is greater than or equal to 1? Well, there's 2 ways you can do this. A long way and say, well, that's the probability that x equals 1 plus the probability that x equals 2 plus the probability that x equals 3 plus the probability that x equals 4, which is these numbers added together, 4/16 plus 6/16 plus 4/16 plus 1/16, which is equal to 15/16. But if you want to find the probability of being greater than or equal to 1, well, that's all the probabilities except the probability that x equals 0. So that's also equal to everything, which is 100% possibility, minus the probabilities that you don't want. And if you want to be greater than or equal to 1, the only thing that's not greater than or equal to 1 is 0. So the whole idea here is that if I'm trying to find all this, I can say, well, it's the whole entire thing, which we know adds up to 1 because it has to, because of how discrete probability works. So it's all this minus the one thing I don't want. That's 1 minus 1/16, which is also 15/16. That works. All right. What's the expected value? So if I flip 4 coins, what do I, so expected value, actually the words make sense. If you flip 4, I should say the word makes sense sometimes. If you roll a single die, right, a 6-sided die, your expected value is 3.5. You're never going to roll a 3.5, right? It just doesn't happen. These numbers are 1, 2, 3, 4, 5, 6. You can't roll 3.5. But the expected value just means that over repeated number of trials, what average do you expect to kind of get closer and closer to as you keep doing it? Sometimes it makes more sense in this kind of context where, well, let's actually find it before I give away the answer. So the expected value here of x, well, again, it's the sum of the values times their probabilities. That's going to be 0 times 1/16 plus 1 times 4/16 plus 2 times 6/16 plus 3 times 4/16 plus 4 times 1/16. That's going to be, let's see, so I get 0, I get 4/16, I get 12/16, I get 12/16, I get 4/16. So adding that up, I get, let's see, 4 plus 12 is 16, plus 4 plus 12 is 16, so I get 32/16. That's the funniest 3 I've ever drawn, which is 2. The expected value numbers don't always come out to be nice, right? Sometimes they come out to be things like 3.5 or 2.7, right? But in this case, if you flip 4 coins, you expect to get 2 heads and 2 tails. Actually, if you flip, and it's kind of interesting. This is something that's also kind of a nice formula. For if all the things have like the same probability of happening, like if you flip 10 coins and each of them have a 1/2 chance of being heads, the expected value is going to be 10 times 1/2 or 5 heads. That's a formula that works. And then we talk about the variance. Sure. The variance, yeah, fine. So the variance of x here is going to be, again, it's the sum of the x values minus the mean squared times the probability of that x value. Again, I'm just going to write it. So my x values were 0, 1, 2, 3, and 4. My mean is 2. So it's going to be 0 minus 2 squared times the probability of a 0, which was 1/16, plus 1 minus 2 squared times the probability of a 1, which was 4/16, plus 2 minus 2 squared times the probability of a 2, which is 6/16, plus 3 minus 2 squared times the probability of 3, which is a 4/16, plus 4 minus 2 squared times the probability of getting 4 heads, which is 1/16. Probably getting 4 heads. So I get 4/16 plus 1 times 4/16 plus 0 times 6/16 plus 1 times 4/16 plus 4 times 1/16, which is going to be 1. So my variance is 1, which means my standard deviation is also 1. So that means we expect to get 2 heads when we flip 4 coins, and the variability is about 1. So you 1 either way. Okay, we got time still. Sure. Let's talk about one more quick example, which shouldn't take too much time. So suppose a game is made in which a player receives $5. So we get $5, flipping 3 heads or 3 tails. Out of 3 coins, but loses $2. $2? Yeah, for anything else. Should you play this game? Over the long run, are you going to win money or not? So the idea here is we want to find the expected value. So we're going to let x equal the amount of dollars that we win. Okay, so we want to find the expected value of x. We want to know, what do we expect to average out winnings-wise? So there are 8 possibilities here. 3 tails, or 2 tails, 1 head. There's 3 ways to get that. Or 2 heads, 1 tail. Or 3 heads. For flipping coins, right, for 3 coins, there's going to be 2 to the third, which is 8 possibilities. So whenever there's something that's a binary choice like this, where it's one thing or the other, if you do it a repeated number of times, the number of total possibilities is just that number 2 raised to however many trials you're doing power. So if you're flipping 6 coins, there's 2 to the 6 total possibilities. Flipping 3 coins, there's 2 to the third, which is 8 possibilities. So let's see. Let's make our little table here. So we have x and we have p of x. So again, x is the dollars we're winning. So we win $5. What probability? What's the probability that we're going to win $5 if you flip 3 coins? How many different ways do I get to win $5? How many ways is that? Out of how many? Guys are like, no, I will not participate today. I'm just here to listen. Okay, fine. Fine, be that way. Sorry. Okay, so we expect to gain $5 2/8 of the time. We expect to lose $2, so we get a negative value if we lose the money. The other rest of the time, 6/8 of the time. So our expected value is the sum of your x values times the probability that they happen. That's going to be x1 times p of x1 plus x2 times p of x2. That's going to be 5 times 2/8 plus -2 times 6/8. So you end up getting 10/8 minus 12/8, which is going to equal -2/8 and -1/4. So what does that mean? Well, it means on average, we expect to lose 25 cents per game, or $0.25 per game. So over time, and so if we played 100 games, we would expect to, on average, or in total, have lost about $25. Interesting. So we shouldn't play this game. Right? If your expected value is negative, you shouldn't play the game.